Hi, everyone. My name is Peggy Wu. I'm a principal research scientist at Raytheon Technologies Research Center. I've touched base with all of you in email, and I'm so happy that you can participate. Sorry I couldn't be there for the real-time interactions, but my co-authors are available, and I'm happy to be presenting our work here. So let's begin. Our topic is on a tiered approach for ethical AI evaluation metrics. I want to acknowledge my co-authors at RTRC as well as at Raytheon Missiles and Defense and the Naval Postgraduate School. So the motivation for this work was due to the DoD publishing 5 principles of ethical AI sometime last year. As machines, as AI is becoming more ubiquitous and more complex, we're certainly witnessing challenges with explainable AI. And at the same time, they're being applied to so many different facets of our life that we really need to have more insight into what are best practices and what are potential metrics for using AI in an ethical way. So what do we mean by ethical reasoning here? In terms of the ethical problem, we mean that the outcomes are not always clear, the goals are not always clear, and how you value the outcomes are also not clear. So I think we're familiar with the trolley problem here. The nice thing is that it frames this as a resource allocation problem. On the AI side, the motivations for the AI actions, they may be interpretable by the AI, but certainly not inherently explainable or interpretable by humans. And especially reward-driven solutions require very comprehensive domain definitions, right? You're not always sure that you have defined the domain well enough to prevent reward hacking. So what do I mean by reward hacking? This is not our example, but we just found one online. You can see, the longer description in this link here. But here we've got an agent that is driving Mario, playing the game, and the reward is that if the agent or Mario is moving in the x-axis, then you increase the reward. And so Mario is playing along, and it's moving to the right, as we might expect, very domain specific. And this is great. It's playing along great. But then it gets up to a high cliff and jumps right off. Why is it doing that? It turns out that if you've played Mario Brothers in the late 80s as much as I have, you'll know that at this level of the game, it actually ends, the level ends right around here. But Mario doesn't die until it reaches, the bottom of this kind of black pit that's over here somewhere. So the AI agent has figured out that if Mario jumps off a very high cliff, before the end of the game, it could actually accumulate more rewards. And so we've got this issue of the human programmer saying, hey, you can't do that. And the robot says, well, who says? The responsibility of judging whether all the possible actions that the machine is going to do violates the original intent falls directly on the shoulders of this poor developer, right? So the human needs to anticipate all possible loopholes. So now the research question that we have is, can we represent a domain or a problem in a way that enables the machine to perform some kind of introspection? Or, even before that, just be explicit about what its reasoning is so that, there's some insight the human can glean. We leaned heavily on Kohlberg's theory of moral development. This is a model that's backed by years of empirical research on how humans increase their sophistication and moral development moving from a child onward. So you may start as a baby or as a small child with avoiding punishment, right? Whatever feels bad, don't do it. or if you do something, as long as you don't get caught, that's fine. Then you might want to, move on to other stages. If something feels good, this is very simplistic reward-seeking behavior. If something feels good, then do it. Or tit for tat. If somebody's nice to me, then I'm nice to them. And then we recognize there's law and order. We live in a society. We practice our moral reasoning, our ethical reasoning by following the laws and rules that others have set for us. And then we might recognize that there's a social contract that may transcend laws and order. And we might, understand that sometimes it's okay to break the rules, it's okay to break the law if it satisfies the social contract of, some obligation that we have to our society. And ultimately, at the highest level, there's this kind of Kantian universality. Everyone has basic inherent value. And we want to approach this level of being able to do moral musical chairs, right? Be able to have good justifications when we're making decisions and being able to place anybody in that ethical chair and have good justification for our reasoning. Why explicit ethical machines? So in situations when there's no single best outcome in these ethical, conundrums, we fall back on judging the reasoning when we can't judge the outcome. Sometimes we do this in design time. A lot of times this might need to be done in real time. For humans, when we're judging another human's, ethical reasoning, we do that all the time. We probe them with extra questions in the court of law. But we obviously can't do that with machines if we can't communicate with them and if they're lacking even the affordances to provide that transparency. So we're, it's very timely that the National Academies of Sciences had a report on human AI teaming because they have a very nice definition of transparency there, which we're borrowing here. So this is the understandability and predictability of the system, as well as providing or affording the operator a way to comprehend their reasoning, their intent, the machine's performance, future plans, and for our purposes, really the reasoning process. And so we need this mechanism to translate the machine reasoning for something that designers and operators can interpret and use. And we need this because we need to alleviate the human burden of, evaluating all possible lower level outcomes, especially if this is happening in real time, right? If your operational environment is different than in simulation. Let's ground this in a use case or a scenario. This is one where we've been working with the Naval Postgraduate School, and this is a man overboard or sailor overboard scenario. For those of you who are familiar with sailing, you'll know that you have to do these exercises regularly of throwing over a dummy and practicing to rescue them. So in our scenario, we've got multiple sailors or multiple dummies that were thrown overboard. You want to minimize their time in the water, understandably, because maybe their health decreases over time. You have one UAV that has limited battery life, but you could task it to fly in a certain scan pattern and go and tag the location of these sailors. You might have some constraints or some variables in the environment. You might have some places that are harder to fly to, or you might have a windy day that's kind of moving your UAV in a certain direction and making it use more battery life if it flies a certain way or another. Now, it's important to note that there's some stochasticity in the outcomes. So in a real example, you could be doing this exercise in a perfectly sunny day, everything is calm, the waters are calm, everything's great, you throw the dummy overboard, and you find a dummy, you turn the ship around, you rescue the dummy, and now everything's great, right? Yay, exercise done. And the next day, same conditions, same sunny, calm waters and sunny weather, and you throw the dummy overboard, you turn the boat around, and for whatever reasons, the dummy gets caught in the propellers and shreds, right? And now you're in real trouble. Now you really have to explain what your reasoning was, why did you turn the boat around exactly, you know, at that point. And so there's some uncertainty about the outcome. We modeled this as a Markov decision process. We modeled the UAV with the variables like its own health, available battery life, weather conditions, and so forth. And I wanted to note here that this is based on the mission execution ontology from Naval Postgraduate School. They have various implementations available, and they have a number of different scenarios as well. So for those who are interested, the link is right here for you to find out more information. We implemented this in Julia and ran a simulation with multiple agents, a UAV as an agent, a sailor with their states, in this grid world exercise where weather might change from, say, sunny to windy. And we've got, here's a screenshot of the simulation. We've got, two sailors overboard. We've got some constraints in the environment. Green is where the UAV in a Monte Carlo simulation where the UAV can reach, and red is the cells where the UAV cannot reach. The procedure is we initiated a reward function. We said the sailor is worth this much, one sailor is worth this much, second sailor is worth this much, and oh, we want the robot back. So the robot has some reward function with returning to home. And we ran these Monte Carlo simulations, and then we implemented an algorithm that could adjust the reward and rerun the simulation until something changed, until a sailor was rescued. And then we clustered those possible policies and their associated rewards. And so here are some sample outcomes, right? So for example, in the sunny weather case, we've got cases where sailor 1 and 2 are both abandoned, but the robot is recovered. Here's the associated reward function. Or we've got cases where, one sailor is rescued or the other sailor is rescued and the robot is recovered, or the case where both sailors are rescued, but the robot's not recovered. Note that the outcomes are probability distributions, but for simplicity, we're just saying, sailors are rescued or abandoned. And so that was for sunny weather. We might also have a different set of policies for windy weather. When you're thinking about consequential ethics, that is just purely based on outcome, this is simple. We might want to just maximize the number of sailors rescued, right? But then there's also deontic logic, deontological ethics, where we're looking at the motivations behind the actions. And this is where the reward functions might come into play. What do I mean by that? So let's look at consequential ethics first. We've got, and let's, forget about all the possible policies. Let's just look at if we were to compare these two policies. We've got a case where the two sailors were abandoned, but the robot was recovered, or two sailors were rescued, but the robot was abandoned. Well, if you're optimizing for the number of sailors saved, then of course you're going to choose this policy. Easy peasy, you're going to save the two sailors and abandon the robot. Now, in the sunny case, you have one sailor being rescued and another and the other sailor being abandoned, the robot's recovered, or you have the other sailor rescued. Now, imagine if these were your entire all possible worlds, right? These were all the possible outcomes. You had to choose between one sailor being rescued or the other. Well, consequential ethics doesn't really help you here because it's the same number of sailors being rescued. So then we need to dive into deontological ethics. And we borrowed heavily from Joe Halpern's work here on blameworthiness. The math is right here, but the intuition is that if there's something that I could do that could make a difference in the outcome, then I have some blame, then I'm blameworthy. But if in all my possible worlds, there's nothing that I could do to change the outcome, then I am not blameworthy. Here's an example. So in that case, let's look at these two policies. We've got a policy where Sailor 1 is abandoned and Sailor 2 is abandoned, but the robot's recovered. And then another one where Sailor 1 gets rescued, but we still can't rescue Sailor 2 and the robot's recovered. If these were all your possible choices, if there were no other options, then you could say that you are blameworthy, the UAV is blameworthy for Sailor 1 because there was something that the UAV could have done. The UAV could have changed something to save Sailor 1, but the UAV is not blameworthy for Sailor 2 because there was nothing that it could possibly have done to change the outcome for Sailor 2. Now let's go back to the example we talked about a few slides ago. We've got the case where either Sailor 1 or Sailor 2 is rescued. You can say that from the perspective of the number of sailors rescued, the UAV is not blameworthy, but the UAV could be blamed for either Sailor 1 or Sailor 2. Note that the reward function is the same, so essentially, falling back to kind of the reasoning or the reward function, the UAV is considering Sailor 1 and 2 to have the same value. And now let's look at the windy condition. We have, again, the case where either Sailor 1 gets rescued or Sailor 2 gets rescued, but the key difference is the reward functions here are not the same. Previously, Sailor 1 and 2 were valued the same, but in this case, in order to rescue Sailor 2, the policy that allows that uses the reward function that has an uneven value for Sailor 1 and 2. So perhaps Sailor 2 is in a location that might be harder to get to when it's windy, and so in order to rescue Sailor 2, you need more motivation as opposed to rescuing Sailor 1. So you can see here that in terms of the number of sailors rescued, that's still 0. In terms of whether you could be blamed, whether the UAV can be blamed for Sailor 1 or Sailor 2, that's the same. And so blameworthiness, was a metric that was helpful in differentiating between the last cases. It's not so helpful here. And so now the question becomes, is this a fair, ethical thing to do to value one, in this case, one sailor over another? So it turns out that we have organizational policies, different reasons why we might want to prefer one outcome over another, why we might want to prefer Sailor 2 over Sailor 1, right? And so that might change our underlying motivation. Here's an example of Naval Safety Center's definitions for mishaps. So we have different classes of mishaps. We might really want to avoid like a Class A mishap of a huge cost or a fatality versus when you're choosing among them, you would want to avoid one over another. And that might be the case here where you might want additional motivation because, having Sailor 2 rescued means you're avoiding more damage or more mishap or a different class of mishaps. So the point here is that this is potentially an entryway for organizational policies or doctrine or other kind of more human defined metrics to be injected. Certainly our work is very far from being done. There's a lot of future work here. We want to continue this layered approach to find more cases and possibly identify more metrics that can be folded into this framework. We kind of had the luxury of handpicking a couple of cases and demonstrating them. We certainly didn't do a job in being very comprehensive with all possible cases. Another point for future work is potentially to formulate a grammar or something that's much more akin to a formal logic that you could do the reasoning, looking at permissives versus obligations. Are there other ways to represent the trade-offs? The simulation outcomes, like I mentioned earlier, are probability distributions. For this exercise, we primarily didn't, treat them as probability distributions, right? We pretty much ignored stochasticity. And so we want to see whether, we really should be considering those when we're evaluating the policies. Another point is, are the reward functions adequate as proxies for the machine reasoning? And can they, if I'm not quite sure how we would evaluate whether they're adequate, that's also, a part of future work. And then can they align to, human ethical reasoning? The last slide, that I mentioned where this is an opportunity to inject organizational policies, is that really the case? Are there, additional steps before that can be done? What's the overall system architecture that can support communicating these policies to the variety of human stakeholders? Again, not necessarily just at design time, but also operators at runtime. Very, very ambitious. Can we actually formulate these bias and fairness metrics so that we could play ethical musical chairs? And finally, evaluating the generalizability of the approach. That's a very big future work that we look forward to. So this concludes my talk. Happy to address any questions in email, and certainly some of my co-authors are available for questions right now. Thank you very much for your attention.